Hello and welcome. In this video, we're going to continue on our journey with solving second-order differential equations. This one specifically will focus on homogeneous, second-order linear differential equations with non-zero damping. So we've already explored this idea that you can have spring mass systems without damping, and now we'll consider adding the damping term, which will result in a slightly different solution process. But let's get into some preliminaries first. These are some tools that we're going to need. So first of all is solving a system of linear equations. So suppose we want to solve this system. So by the definition or by the description, system just means there's more than one equation to be solved. And they are linear, obviously, because you could get them in the form y equals mx plus b. And what we want to do is we want to find a solution, a pair of values, x and y, that make the equations simultaneously true. So you can look at this and you can say, well, 5 plus 5 equals 10. And so x equals 5, y equals 5 satisfies the first equation. But it does not satisfy the second one because 2 times 5 plus 3 times 5 is 25 and not 23. So 5 and 5 don't quite work. There are a couple of ways you can solve this. One way is to drop both of the equations into a graphing application and find their intersection point. So here we see that 7, 3 is the point that both equations share in common. And so geometrically, the solution is the point that they have in common, which is the intersection point. So that 7, 3 is on both lines, therefore 7 plus 3 equals 10, and 2 times 7 is 14, 3 times 3 is 9, 14 plus 9 is 23. So that point 7, 3 makes both equations true. Now that's one way to solve it, is to graph them and find the intersection point. The other way is to, one other way you may have seen before is called substitution. And so if you solve one of the equations for one of the variables, for example, x plus y equals 10, if we simply subtract y from both sides, we get x is equal to 10 minus y. Now what we can do with that is, because this x is the same as this x down here, I can actually substitute in 10 minus y in for x. So let's go ahead and do that. 2 times x, so this is 10 minus y. And now you can see that we've obtained an equation that now only depends on y. So we do some distribution, 20 minus 2y plus 3y equals 23, which gives us 20 plus y equals 23, or y equals 3. Now at that point, once you find the y value that both equations have in common, you can plug y equals 3 back into either of the two equations and solve for x, but this one's already solved for x, so why not just say x equals 10 minus y? So since y is equal to 3, we're going to go ahead and substitute that out for 3, and 10 minus 3 is 7. So x equals 7, y equals 3 is the solution. Now, if you had plugged in y equals 3 up here, let's say 2 times x plus 3 times 3 equals 23, and solved for x, you would get exactly the same answer. You get 2x equals 14 and x equals 7, which is the same answer we got here. So once you find one of the values that they share in common, the other value corresponds to the value you've already found. Therefore, it's not important which one you plug it into. Anyway, but the point is, this is unnecessary. It's just extra algebra. We don't want to get tied up in that. So you can also just enter the two equations in, separated by a comma, into Wolfram alpha, and you get the solution that shows up. It even shows you a beautiful graph of those intersection points. All right, so now we're ready to go on, because we're going to need to solve a system of equations. As you've seen with velocity and initial position, we had two equations. Fortunately for us, those reduce down very easily to solve for K1 and K2, but sometimes you get a system of equations where you do have to find the point that both equations have in common. So consider a spring mass system. Now we're going to assume that we have a spring constant of 2. If we're in the metric system, this is measured in newtons per meter. So the amount of force that the spring applies for every meter of displacement. And you can also see this here, and just in case you want a little bit of intuition behind this, the spring force is negatively proportional to y. So that means that if you want to determine your spring force and k is 2, now you just have to think about your displacement. So you can see that the spring force, which is measured in newtons, is going to be -2 times the displacement. So for every 1 meter you increase y by, the spring force will get bigger by a factor of 2 newtons. So that also helps justify this newtons per meter. Now this is the force per unit of velocity. So the faster this spring mass system is moving, the greater the decrease in speed that will be caused by the damping coefficient. So it's going to slow the spring mass system down. So ideally, if you kind of imagine that this is the spring mass system, and here you have a mass, and this thing is going to be kind of going, let's say it starts by going down, and then it goes up, and then it goes down, and then because of the damping factor, we probably expect this mass to slowly stop oscillating and come to a rest. And then we have m equals, excuse me, not 0, m equals 1. And that would be measured in kilograms. Now these are not necessarily realistic values. Right now we're just learning how to work with these. Obviously having 1 kilogram mass may be a lot heavier than our spring mass system, or maybe not heavy enough. So then when we plug in, here we have, this is b over m, and this is k over m, so 3 over 1 and 2 over 1. Now, unfortunately for us, because now we have this middle term in here, sine and cosine don't work. And the reason these won't work is because, for example, if we said y1, our initial guess is of the form y1 equals sine of even something t. So even if we didn't know what that was going to be, what constant argument we were going to have there, we could say, well, y prime equals b cosine of bt. And y1 double prime is equal to -b squared sine of bt. Now the problem we're going to have when we come over here and we plug these components in is that you're going to see that now we have a mixture of sines and cosines. So y double prime is -b squared sine of bt plus 3b cosine of bt plus 2 sine of bt equals 0, and there's no way these three things can add up to 0, because remember, sine, the basic sine function is going to look like this, but the cosine function looks like this. So these guys are not in the same phase, and therefore they're not always going to be able to sum to 0. So these will not equal 0 because of the fact that we have 2 sines and we have 1 cosine in here, and those are not like terms, so they will not combine. So the only other function that we know of, so barring this, if this term were missing, sine and cosine would work. But with that term there, sine and cosine will not work, so we resort to things that we already know. Well, what kinds of things can we add to its derivatives, or what kind of function can we add to its derivatives, and they're all like terms? Well, exponential functions, when you take their derivative, the derivative of an exponential is always another exponential with the same exponent. Therefore, let's try this approach. Let's say, you know what, sine and cosine aren't going to work because the first derivative is going to not be able to cancel with the function and its second derivative. So we're going to use the method of undetermined coefficients. Now this just means that we don't know exactly what value of r will work here, but with y equals e to the rt as the base function, assume that y of 0 equals 0, y prime of 0 equals -1. Graph the solution, is it what we would expect? Okay, so we know from our equation, it's y double prime plus 3y prime plus 2y equals 0. Now, our guess is of the form y equals e to the rt. Now, the beauty of this is that if the guess is wrong, the mathematics simply will not work out. Just like up here, we said, oh, it's going to be sine of bt, and then we run into a problem. We can't actually find a value of b that will cause these three functions to add up to 0. So if something goes wrong, if this is the wrong guess, the mathematics will let us know. So the derivative of e to the rt is r times e to the rt by the chain rule. And the second derivative of that is r times r, which is r squared e to the rt. So now what I'm going to do is I'm going to solve for r. Solve for r. And the way in which we're going to do that is we're going to say, well, y double prime is r squared e to the rt. Now we have that 3y is going to be 3 times r e to the rt. So 3r e to the rt. And then 2y, which is this guy here, that's going to be 2 times e to the rt. So we'll have plus 2e to the rt. And we know that these three things have to add up to 0. Now you see that this is going to be possible because they're all common, they're all like terms, right? This has the e to the rt, this has e to the rt, this has e to the rt. Here I have r squared of them, here I have 3r of them, here I have 2 of them. So if I'm going to add like terms, I'm going to add their coefficients. Again, another way you could view this as is if you factor out e to the rt, you get r squared plus 3r plus 2, and that all equals 0. Now again, another way of thinking about that is I have r squared copies of e to the rt plus 3r more plus 2 more, and so we just approached it via factoring, but it is simply a matter of adding the coefficients together. Now e to the rt, if you think about that function, the only way two things multiplied together can be 0 is if one is 0 or the other is 0. Now e to the rt never equals 0. Now that's because even e to the rt does one of a couple of different things. It either grows exponentially or it's going to decay exponentially. So that could look like this. All right, so those are kind of our two options there. And if it grows, then obviously it's not going to approach 0. And there's no number you could raise something to in order to get 0. So e to the 0 is 1, e to the negative 1 is 1 over e. So these functions will never equal 0. So anyway, the point is, the only way for this product to be 0 is if r squared plus 3r plus 2 is equal to 0. Perfect. Well, I know how to solve this. This is a quadratic function. This is a quadratic function, which means I can solve it one of a couple of different ways. I can use the quadratic formula. So you can use quadratic formula, which recall that to solve this equation, it would be negative b plus or minus the square root of b squared minus 4ac over 2a. Another way to solve this is to graph this parabola. This is going to be a parabolic function, and then find out where the roots are, where this function intersects the x-axis. So we're looking for 2 points. The other way you could do it is just by using some sort of Wolfram alpha or something. Type this in and it will solve it for you. So if you just typed in r squared plus 3r plus 2 equals 0 into Wolfram alpha, that would solve it as well. So I'll just put a third here, Wolfram alpha. And you would just type in r squared plus 3r plus 2 equals 0. And even a fourth way that we haven't described is factoring. Now, if you're not sharp on your factoring skills, you may not want to try that, but this one does actually factor nicely. R squared plus 3r plus 2 factors into r plus 2 times r plus 1 equals 0. And the trick behind factoring here is these two constants have to multiply to give me 2 and have to add to give me 3. And so that works out, so I get r equals negative 2 and r equals negative 1. Now I don't want to treat those as the same, so I'll call this r1 and r2. Which one's which does not make any difference. So that means I have two solutions. As we've stated before, we said that second order equations have two solutions. And guess what? This is why. Because whenever you go about solving equations like this, you're going to end up solving a quadratic. So we have y1 is equal to e to the negative 2t, so that's r1, and y2 is equal to e to the negative 1t. Now by superposition, by the superposition theorem, we know that if you have a homogeneous differential equation and you find two solutions, any constant multiple of the first solution plus any constant multiple of the second solution is also a solution. And there is our spring mass system solution. Now what we need to do is, sorry, this kind of look a little messy. Now we just need to satisfy the initial conditions. And to do that, we see that our initial position is 0 and our initial velocity is -1. So remember, this is position. In the same way, we need to find the velocity function, which is the derivative of the position function. So the derivative of this will be -2 k1 e to the -2t minus 1 k2 e to the -t because of the chain rule. And now we can plug in our initial position, which is 0 at time 0, plus k2 e to the -0. And our initial velocity is -1, so we'll plug in -1 for the initial velocity, -2 k1 e to the -2 times 0, minus k2 e to the -0. Now the nice part about these exponentials is that e to the 0 is 1, so we have two equations. This one right here is going to give me 0 equals k1 plus k2 for this equation, and this one will give me -1 equals -2 k1 minus k2. And this system of equations right here is exactly what we were doing in our preliminaries. We want to solve this system of equations so that we can figure out what k1 and k2 are. So I'll go ahead and do this in Wolfram Alpha. And here you can see that now, entering the equations in, I just like to type k1, k2. Sometimes you work trying to do an underscore, makes Wolfram Alpha give you some odd output. Just make sure it interprets it. These brackets mean set. It's the set of equations. And Wolfram naturally knows that if you give it a set of equations that you're often looking for a solution. So we get k1 equals 1, k2 equals -1. So that means our final solution is going to be y equals k1 e to the -2t plus k2, which is -1, e to the -t. And this is how our spring mass system, its position, occurs over time. Before we go and graph this and see what's happening here, what do we expect? Well, first of all, we see that we have damping, right? So damping is likely going to cause that spring mass system to settle down. For faster or for slower, we don't know yet, because we don't quite understand the magnitude of these numbers. But if we go ahead and graph this, we should see that this spring mass system is going to come to rest. Does the function support that? Well, there's no sines, there's no cosines in our equation, so there's not going to be any oscillation going on here, or any significant oscillation. So these are both decaying exponential functions. And so we can see here that as t approaches infinity, y approaches, well, what happens to this term? Well, as t approaches infinity, this is going to decay to 0. This is going to decay to 0. So that means y is going to decay down to 0. And sometimes whenever you do these limit analyses, just look at each of the terms and ask yourself what's happening to it as t gets bigger. And if the answer is it goes to 0, then your position is ultimately going to come to rest. So let's go ahead and plot this in Desmos. So here you see it. There's the initial position. Now our initial velocity was negative, and since initial velocity is negative, that means in our graph we expect a negative initial rate of change means the graph should go down. But also that means that the spring is being compressed initially. So it's at rest at the moment, but if we press play on our video, then that spring mass system is going to start going down. And again, what I'll do is I'll just insert a slider here, and we'll just look at this over the first 8 seconds or so. And then here I'll just make sure it does it just once, and I'm going to slow it down a bit. And now I'm going to look at the point 0, comma, f of t. And I'll also just look at the point t, comma, f of t. All right, so before we look at the actual observance of how the mass moves, let's just follow this point. So there's a little bit of a compression and back to rest. Now let's go ahead and add in sort of this green point, which we'll think about as the mass itself. It starts off at rest, and watch what happens over time. So the mass compresses a little bit and then returns to rest. So there's no oscillation in that spring whatsoever. And if we go ahead and plot both of the points, and we can see there's that point coming back to rest, a very non-entertaining spring mass system, and maybe not something you'd want in your car as a suspension system, because going over that speed bump would feel very odd, to say the least. So backtracking here for just a moment, the reason we had to choose this new method, and you can see kind of why this method has undetermined coefficients. It was the value of r, that coefficient that we did not know, and we were able to successfully solve for that. Now the reason we had to guess e to the rt as the base function, which by the way, exponentials and sinusoidals are going to be the most common functions we run across. So if all else fails, those are often the turn to guesses: sine, cosine, exponential. So the reason we had to guess exponential in this case was, once again, because we had to find a function that, when added to its first derivative and its second derivative with these coefficients, they canceled out and gave us 0. Sine wouldn't work because now having to have the first derivative in this equation, whereas remember without damping this whole term was 0, we introduce a cosine amongst the sines, and those cannot add up and cancel to give us 0. So e to the rt, what we did is we said, all right, well, e to the rt, let's just find the right r that does this. So if y is e to the rt, its derivative is r e to the rt, second derivative r squared e to the rt, and then we substitute in for those components and we solve for r. One of the interesting things to note already is if you look at this equation here, which is often called the auxiliary equation. This is called the auxiliary equation because it's often just used to solve for something within the problem that's important. And this auxiliary equation, if you notice, its coefficients are 1, 3, 2. Well, those just happen to be the same coefficients in front of the first, or the second, the first derivative, and the original function, 1, 3, 2. So let's see if we can, before we take off with that pattern and just assume that that's all we have to do, is to solve r squared plus whatever coefficient is there, r plus whatever coefficient is there equals 0. And then once we had those two values of r that we solved, in this case this was factorable, then we constructed our two solutions because we have two values of r, so two different exponentials will work, one with negative 2t and one with negative 1t. By the superposition theorem, if you're dealing with a homogeneous differential equation, their sum is also a solution, and any constant multiple of the first function plus any constant multiple of the second function is a solution. And then we just used our position initial condition to form one of our equations. We had to take the derivative to get the velocity function, find the values of k1 and k2 that made both of those true, and we had our final solution that was then graphable. And I encourage you to think about limits like this. You don't have to get into calculus 1 type of limits, but oftentimes you can look at the function and just entertain the idea of what happens as t gets larger and larger. All right, suppose you have a suspension on a small children's electric scooter. The child averages that it's going to ride the scooter 20 kilograms on a spring that is rated at 40 newtons per meter and a strut that damps 80 newtons per meter per second. Initially, the spring is at rest, and a speed bump causes the spring to compress at a rate of 0.1 meters per second. Find the equation of the movement of the child on the scooter. Graph the solution. Is it what we expected? So here we see that we have a mass that's going to be 20 kilograms. We have a spring constant, which is rated at 40 newtons per meter. And we have a damping coefficient, some sort of strut suspension assembly that's 80 newtons per meter per second. And so again, we have some sort of scooter here. There's the handlebars on that scooter, and it's going to have some sort of suspension in here, some sort of spring between the wheels and the scooter itself. And then we're going to have of course, it's got to be a stick figure child. And the child is going to ride this thing down the street. Okay, great. So we also have our initial conditions. We have that y of 0 equals 0. The spring is at rest, so nothing's happened yet, but just bumped into a speed bump. It's going to cause the spring to compress at a rate of 0.1 meters per second. So our equation is going to be the second derivative plus b over m, which is 80 over 20. That equals 4. Y prime k plus k over m, 40 over 20, which is 2, and that equals 0. And our initial conditions are the initial position is 0, and the initial rate of change is negative 0.1. Why? Because it's going across a speed bump, it's going to compress at a rate of 0.1 meters per second. So that's moving in the negative direction. And okay, so here, let's go through our guess process again. So we see that it has the first derivative in addition to the second derivative in the original function. So our guess is of the form e to the rt. Its derivative is r e to the rt. Its derivative is r squared e to the rt. And you notice that the reason these squares are coming about is not because of the second derivative itself, but because of the chain rule being applied twice, which creates two factors of r. So that's an important thing to know. Just because you see a second derivative does not mean that involves a square at all. I know it's confusing because when we look at the second derivative, you want to read that as d squared y dt squared. It's not a square. It just means the derivative of a derivative. Fortunately for us, it works out to be leading into a square. So now substituting in for y double prime, so r squared e to the rt. For y prime, we'd have 4r e to the rt plus 2y plus 2 e to the rt equals 0. Once again, we'll factor out our e to the rt. R squared plus 4r plus 2 equals 0. And you can see here, again, this will never be 0. So our auxiliary equation is going to be r squared plus 4r plus 2 equals 0. This one is not as easily factorable because I can't really find two numbers that will add to 4 and simultaneously multiply to give me 2. So I can use quadratic formula here. And quadratic formula will tell me that, or again, I could use Wolfram alpha. Wolfram alpha, you just enter this equation in as it is, but let's just go ahead and solve it. Why not? So r is going to equal this on top negative b, so there's my b, plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is 2, divided by 2a, which is 2 times 1. So cleaning that up a bit gives me negative 4 plus or minus the square root of 16 minus 8 is 8 over 2. And so this is going to give me two approximations. We're gonna give them an approximate form. Mainly the reason we do this is because it's just easier to work with, and we're not having to be super precise to, let's say, 10 or 15 decimal places. So we'll say it's about negative 3.4. And R2, so that's going to be negative 4 minus the square root of 8 over 2. And negative 4 plus the square root of 8 over 2 will give me about negative 0.6. Perfect. So that gives us our solutions to work with. So now that we know what the R values are, I'm just going to go ahead and jump straight to the superposition theorem. It's going to be K1 e to the R1t, which is negative 3.4, plus K2 e to the negative 0.6t. Now remember, Y1 is e to the negative 3.4t y2 is e to the negative 0.6t, but by superposition, any constant multiple sum of the two functions is a solution. So this is my position, and story is the same. Position means we need to look at the initial position, which is 0. And when we plug in 0 for t, the beauty of working with exponentials is this is just going to become k1 plus k2. Now for the velocity function, the derivative of this is going to be negative 3.4 k1 e to the negative 3.4 t minus 0.6 k2 e to the negative 0.6 t. And we know that this is negative 0.1. This is going to give us negative 3.4 k1 minus 0.6 k2. And this is the system of equations that we need to solve right here and right here. And there we go, there's our value of k1 and k2. So we have as our final solution y equals k1, which is about 0.04 or 0.04 e to the negative 3.4 t plus k2, which is minus 0.04 e to the negative 0.6 t. Now once again, we should expect very similar behavior. That we're going to have decay in both terms, so as t gets infinitely large, well, y is going to approach, that term is going to approach 0, this is going to decay to 0, and so together we're going to see this spring mass system come to a rest. If we come back over to Desmos, we get something very similar, and this one's not super, this one's even a little bit less exciting because, well, that spring mass system just again compresses a little bit, comes back to rest. Does not do any stretching. The reason we can try to understand this, or the way we can try to understand this, is there's the damping coefficient is sizably large, and so probably what's happening is the system is a little bit overdamped. So there are such things as having an overdamped or underdamped system. So the other thing we should just point out is again checking those initial conditions by even just scoping out the graph, making sure that your initial position is 0, 0, and then because we have just a very slight negative initial rate of change, probably explains the difference between this massive oscillation here and just this very subtle oscillation. There's enough damping to where this initial velocity is just not very strong. Just imagine that you push a spring on your car just very lightly and with a very low speed. You're not going to get very much oscillation at all. So if we zoomed in on this, we could really make this pronounced. But you see that relatively speaking, this one almost compresses down to almost, what about 0.125, almost a quarter of a meter. This one doesn't come even close to that. Now at this point, we might have a hunch as to how we can solve a lot of these differential equations. So I don't want to just limit us to just talking about spring mass systems. This could be any second order equation where we have the second derivative plus some constant times the first derivative plus some constant times y equals 0. Now for us, this constant here is the damping coefficient divided by the mass, and this is the spring constant divided by the mass, but again, we don't have to limit ourselves to just studying spring mass systems. So one thing that we're speculating here is that the solution is going to have this form, k1 e to the r1t plus k2 e to the r2t. That's been our observation in the last two examples. Now what are r1 and r2? Well, those are roots of the equation r squared plus c times r plus d equals 0. So we do have that observation now that the coefficients of y double prime, y prime, and y are going to be the coefficients of r squared, r, and the constant term. And once we solve that, we have our value of r1 and r2 that satisfy the solution, and then we can solve for k1 and k2 using initial conditions. So we have already been using this regularly. However, what happens when the roots have imaginary parts? Anytime you solve a quadratic, sometimes your parabola does not have any real roots. So we've observed situations in our past where, for one, well, you could have two roots, like this and like this, or it could be going downwards. So this has two, what we would call real roots. Another situation is where you only have one real root, right? We're not going to spend much time on the one real root situation because the chances that we have exactly one point where our parabola touches is not very common. And then the third case is where you have no roots, no real roots. And all that means is that you have two imaginary roots, or two complex roots. So let's say that we wanted to solve this quadratic equation here. So we would start off by saying x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And that gives us negative 4 plus or minus the square root of 84. I think that comes out to negative 100. Negative 100 plus 16 is negative 84. Okay, and that's all over 2 times a. Now, you see that we have a square root of a negative. So the one thing that I could do here is continue to break this down and write this as negative 4 plus or minus the square root of negative 1 times positive 84 all over 2. Now, if you take the square root of a multiplication of two things, what we know from algebra is that that is the same thing as taking the square root of negative 1, multiplying it by the square root of 84. This does not work if it's addition or subtraction, it's only if it's multiplication or division. All over 2. Okay, now the square root of negative 1, we know that that's an imaginary number. Because what number times itself gives me negative 1? Well, I could do 1 times 1, which is positive 1, or negative 1 times negative 1, which is still positive 1. So we give this guy a name. We call this I. And I just stands for the square root of negative 1. So that's just the symbol we use in place of that. So here we're going to have negative 4 plus or minus, now the square root of 84 I could approximate, but I'm just going to leave it as the square root of 84, multiplied by I all over 2. So because I have a plus or minus, I'll divide this by 2, I'll divide this by 2, and now I see that my root to this equation is I have negative 2 plus or minus the square root of 84 over 2 times I. All right, so we have two pieces to this puzzle. First of all, we see that anytime we have complex roots, it's not super hard to see that we're going to have both of our roots are going to be of the form a plus or minus bi. So like here our a is, I'll use a different color. Here our a is negative 2, and our b is square root of 84 over 2. So these are going to become important. A is called the real part, okay, and they come in complex conjugates, meaning that you'll have a plus bi and you'll have a minus bi, and that's always true if you're going to have complex roots. So a itself, negative 2, is called the real part because it's the real part of this complex number. A complex number could have a real part, an imaginary part, or both. And b is called the imaginary part. Now, people want to say it's square root of 84 over 2i is the imaginary part, but no, we're referring to just the coefficient, square root of 84 over 2. So this is equal to, that's equal to a, that's a right there, and this number right here is b. Together, a plus or minus bi is called a complex number. Now, we'll prove this at the end of the lesson, but for all intents and purposes, just to be able to demonstrate this, let's go ahead and state the theorem first. So what happens if you have complex roots? Well, consider our differential equation. This is the same thing as what we were dealing with up here. up at the top, except now suppose the roots of the equation r squared plus cr plus d equals 0 are complex, such that the value of r that you find is a plus or minus bi. Then the general solution is as follows. Y equals k1 e to the at, so notice that a is, whatever a is, that's going to go here, and it's going to go here. K1 e to the at sine of bt. So b is there, and so b goes there, and b goes there, and that's going to form your general solution. So it's kind of fun to see that if you have complex roots, you have a mixture of exponential and sinusoidal functions. Let's go ahead and put this to play and see how this works. So here we have y double prime plus 4y prime plus 25y equals 0. So again, our guess, just to see how this guess evolves, would be y equals e to the rt, so y prime equals r e to the rt, and y double prime equals r squared e to the rt. And when we plug these components in, we get r squared e to the rt plus 4r e to the rt plus 25 e to the rt equals 0. And again, you see we factor out e to the rt. This part's very consistent regardless of whether or not you're going to have real or complex roots. We just don't quite know yet. Now we find the roots of this guy. I'm going to go ahead and jump to Wolfram Alpha and do this, since I don't really feel like computing it. Now, as mentioned, using Wolfram Alpha, you can just enter it in as you see here, and it comes up with two complex roots. Now this is the same equation that we were solving up here. We were just using x. We didn't quite get the same answer, which is sort of odd. They came up with -2 plus or minus the square root of 21 times I, but we came up with -2 plus or minus the square root of 84 over 2 times I. And it turns out that you can actually reduce this further. -2 plus or minus, you can actually break up 84 into two factors, the square root of 4 times the square root of 21. And that's over 2, and that's over 2 times I. Square root of 4 is 2. 2 over 2 cancels, and so you see we get, not -2. This is not -2 over 2, just -2. And so you see we get -2 plus or minus the square root of 21 times I. So same thing Wolfram Alpha gives us. Wolfram Alpha reduces it for us quite nicely. All right, so our value of r is -2 plus or minus the square root of 21 times I. So we want to identify our a and our b. Here our a is -2. Our b is square root of 21. Notice that b is always going to be the unsigned value, so there's always going to be a plus or minus here, but you're just taking the positive square root of 21. And so our general solution is going to be y equals k1 e to the at sine of bt plus k2 e to the at cosine of bt. And once again, now we can satisfy our initial conditions. Here's where things get a little messy, just because taking the derivative of this requires using the product rule. So this is the position, and let me just go ahead and set that up. We know that the initial position is 1, so 1 equals. Now here's the nice part. K1 e to the 0, that's just going to be K1, but sine of 0 is 0, so this will be 0 plus e to the 0 is 1, cosine of 0 is 1, so this will just be K1 equals 1. Perfect. So that solves for our K1 value. Now to get velocity, we have to take the derivative of this function, and that's where I just said it gets a little bit messy. So by the product rule, it's f prime g plus fg prime. So k1, the derivative of e to the -2t is -2 e to the -2t. Second function untouched. Plus the first function times the derivative of the second, which is going to be the square root of 21 cosine of the square root of 21t. And then we have to take the derivative of this whole second term, which will be very similar, plus -2 k2 e to the -2t cosine square root of 21t. That's the derivative of e to the negative 2t times cosine untouched, plus the first untouched times the derivative of the second, which will give us a negative, since the derivative of cosine is negative sine, and it'll be negative square root of 21, k2 e to the negative 2t sine of square root of 21t. So it gets a little bit messy because of that two product rules in there. But now we can substitute in our initial velocity, which is 0. Well, this should be y prime. So 0 equals, and if we look at these terms term by term, the signs are going to be 0 because you plug in 0, sine of 0, 0. And so then we can, so that'll be 0, this will be 0. This will give us e to the 0 times cosine of 0, that's 1. So that will leave us with square root of 21 k1. And this term here, e to the 0 is 1, cosine of 0 is 1, minus 2 k2. Now I could dump this into Wolfram Alpha, but this is a really quick solve. If I just plug in k1 equals 1, I'll have 0 equals square root of 21 times 1 minus 2 k2. And subtracting that over, dividing by 2 gives me k2 equals square root of 21 over 2. So now my final solution is just going to be a matter of replacing k1 and k2 in my original solution. So I'm going to go ahead and just lasso this guy here and replace k1 and k2. All right, so k1 we just said was equal to 1. And k2 is equal to the square root of 21 over 2. You can approximate that if you want. I'm just going to leave it as that since I have square root of 21 in here. So let's go ahead and graph this and see what happens. Now, we do have sine and cosine in here, but the other thing that we should note is that this coefficient, that the coefficient of a sine or cosine function controls the amplitude. So these guys here are going to be related to the amplitude. Now, the thing is, amplitude doesn't always have to be constant. So as t gets larger and larger, the amplitude is going to get smaller and smaller at an exponential rate. So what we're probably going to see is we're going to see some oscillations that are going to slowly or quickly fizzle out over time. Now here we have that graph. You can see that our initial position, I did catch a little mistake here before we do that. Here, this should have been k2. Maybe you caught that already. It should be k2 is equal to 1. k2. Apologies for that. And then here, this means that this statement is still going to be true, but we should replace k2 with 1 and leave this unbeknownst. So let's go ahead and resolve this. So this should be 0 equals square root of 21 k1 minus 2k2, which is just negative 2. Add that to the other side, divide by square root of 21. We get 2 over the square root of 21. So it's just going to invert our fraction here. 2 over the square root of 21. All right, change that back here. 2 over square root 21. And now that looks a little better. And I think we'll get this eventually. So k1 should actually be 2 over the square root of 21, and k2 is 1. So, and the reason I knew that is because my initial condition was kind of off. So when you do notice your initial condition is off, that usually is a good indicator that something is not quite right. So we'll go ahead and put that back over here. There's our 2 over the square root of 21. So there's our initial position. We have an initial decrease in the rate of change, and watch what happens to that spring mass over time. That green thing starts at rest and oscillates a little bit and then quickly returns back to rest. Now we can slow that down just a little bit more, and so you can see it in all its glory. A little bit of so we start off with the spring mass system is stretched 1 meter from its displacement. returns to rest, compression, a little bit of a stretch, returns to rest, a little bit of a compression, returns to rest again. We can make this difference seem as large as we want. If we zoom in on it, you can see that it's still continuing to oscillate forever and ever and ever, but it happens really quickly. Now, the reason this is happening so fast is because our decay rate is 200%. But if we made this, for instance, negative 0.2, let's just say hypothetically that's what our A value was, you still get that exponential decay in the peaks. You can see that the peaks are kind of getting smaller by an exponential factor, and if that decay rate is a lot smaller in the spring mass system, usually it's caused because of the damping. Your damping isn't that strong, so the mass is able to oscillate more. But in our case, our A value is a lot larger, and as a result, we get these very fast decays. So that gives us a good sense of how to solve systems with complex roots. We will derive the why this works at the end of the video in case you're intuitively curious how that works. It is a very beautiful mathematical process. Let's just spend a moment to focusing on the types of solutions we have. And we notice that when we find these roots of our spring mass system, which looks like this as an equation, when we found the roots of r squared plus b over m r plus k over m equals 0, that was our auxiliary equation. That's our auxiliary equation. Then we found that we had to use something like the quadratic formula. Now that's going to be negative of the b value, which is b over m, plus or minus the square root of the b value squared, so that's b over m quantity squared, minus 4 times a times c, all over 2a. Now the number of roots is really what we're after here. When we have, the way we determine the number of roots is by this thing that we call the discriminant. So this thing here, this quantity under the radical, this is called the discriminant. And depending on where that is, relative to 0, so if this quantity down here is bigger than 0, that is, it's a positive number, then we're going to have two real solutions. If this number is negative, then we're going to have complex solutions, and if it's equal to 0, we're going to have a repeated root. Then we'll have negative b over m plus or minus 0 over 2. And negative b over m plus 0 and minus 0 produces the same result. So if we look at that and we ask ourselves, okay, when will this quantity be negative? So if we look at when will b over m squared minus 4 times k over m, when will that be negative? Well, in terms of the b value, if I do a little bit of algebra on this, I see that this is b squared over m squared, which is less than positive 4km. Right, so if you add things about the inequality, it still maintains the truthfulness of the inequality. If I multiply both sides by the square of mass squared here, and mass squared over here, that's a positive number, so that's not going to change the sign of our inequality. The masses will cancel out here, and that will lead me to b squared has to be less than 4 times k times m. So if b squared is less than 4 times k times m, or 4 times m times k, we have what's called underdamping. B is small relative to m and k. Now we saw an example of underdamping here. This is called underdamping. And this happens precisely whenever you end up with complex roots. So you'll have complex roots, and your solution will be of the form k1 e to the at sine bt plus k2 e to the at cosine of bt. All right, so that's going to be the underdamped situation where you're going to have some oscillation. And that leads to complex roots. So we call this type of system an underdamped system. Now, overdamping is usually whenever your damper is really large and causes your spring mass system to immediately return to rest. That's going to happen anytime you have real roots. So if we just change this to a greater than sign, this means that the system is going to have two real roots. And we already know that if we have two real roots, our solution is of the form k1 e to the r1t plus k2 e to the r2t. And that's going to be called an overdamping of the system. And so that's going to be, again, so up here, our graph visual will look something more like this, where you do have decay, but it takes a little bit of time. With two real roots, the example we encountered is where something like that, where it almost immediately stabilizes out, or doesn't oscillate whatsoever. Now this is the case that we won't really cover. This is called critical damping, and this is where B is just between over and under damping. Here we have two real roots, but they'll be repeated roots, because if B squared is equal to 4mk, what that means mathematically is that if that's the case, then this square root will be 0, and then you'll have two repeated roots, where your roots will be r1 and r2, but they'll all be equal. And we're not going to prove this right now, we're not even going to work with this solution, but whenever you have the same root twice, it doesn't make sense to just write e to the rt plus k2 e to the rt, because that's really just one term. So it turns out that if you have a repeated root, it can be proven that the second solution will be t e to the rt. We're not going to focus too much on this, but you can see cases of where this will happen. Alright, so we're finally ready to derive this complex roots theorem. In order to derive why the solution is y equals k1 e to the at sine bt plus k2 e to the at cosine bt, has to do with the superposition theorem and as well as the linearity principle. All right, so in order to use this, we have to use Euler's identity, which says that e raised to the theta I is equal to cosine of theta plus I sine theta. So let's just say that our roots that we get are a plus or minus bi. So that means we're going to have two solutions. We're going to have y1 equals e to the a plus bi, and y2 is going to equal e to the a minus bi. Now that's all fine, right? That is the solution. Oh, I'm sorry, times t. It's our root times t. And that is our solution, but the problem is we have an imaginary number in there. So you can't really go and graph this on a real number plane. Now, using properties of exponents, I can break this up into e to the at times e to the bti. All right, so distribute the t in, you get at and then bti. And then by property of exponents, we know that if you have common bases, you can add their exponents, but you can also work backwards and split it back up into two factors, which is what we're doing here. I'll do this in tandem because this is going to be the same process, except this will be e to the at times e to the negative bti. And so if we believe or trust Euler on this famous identity, then that means that e to the theta I, this bt is like our theta, and so if we apply this identity to just this second factor here, we're going to have e to the at times, and so again our theta is this bt right there, so that whole thing will expand into cosine of bt, and you can kind of see where that cosine and sine of bt are coming from, plus I times sine of bt. And the same thing will apply over for y2. That will be e to the at, but multiplied by cosine of negative bt plus I sine of negative bt. So there's our y1 and there's our y2. Now again, they still involve imaginary roots, but at least the imaginary number is no longer in an exponent. So that's one of the advantages of Euler's identity, is it allows us to take the imaginary number and write it as a coefficient instead of as an exponent. Okay, so here's what we're going to observe. We know that, first of all, also here, cosine of negative bt from an identity that we know in trig, or that we maybe don't remember all that well, is that if you have cosine of a negative angle is equal to cosine of the positive angle. So if here is a theta, and that value right there is going to be the same value as negative theta, which would be that guy right there. So by that identity, e to the at, cosine of negative bt is the same thing as cosine of positive bt. bt is just the name of the angle. Sine, on the other hand, looks like this. So for the positive theta, you have some number, but then for the same but opposite theta, you have the negative of the number. So that means that sine of negative bt will be the negative of the sine of positive bt. And so what that does is now we see that these two solutions are very similar. So we have y1 equals e to the at cosine bt plus I times e to the at sine bt. And our second solution here, y2, is equal to e to the at cosine bt minus I e to the at sine bt. So those are our two solutions, and still they have that imaginary number in there. But what the linearity principle tells me is that any combination of two solutions, any linear combination of two solutions is also a solution. So that means if I take these and I combine them by scaling and adding them, then I will be able to come up with another solution. So let's call this y1 star. And that star is just going to indicate this is going to be our brand new y1. And what I'm going to do is to create that, I'm going to take 1/2 of y1 and add 1/2 of y2. Now, why did I pick a half? Well, you'll see in just a moment what happens when I pick a half. So 1/2 of this guy plus 1/2 of this guy will give me 1/2 e to the at cosine bt plus 1/2 of this. And when I add these two together, because this will have a 1/2 and this will have a 1/2, they will add together to give us a whole e to the at cosine bt. And whenever you take 1/2 of this plus 1/2 of this, notice that they're equal but opposite signs, so that will give us plus 0. And so our y1 star has successfully eliminated the imaginary number. Now, there's nothing wrong with doing that. An imaginary number still acts and is treated just like a constant. So just because you see an I in an equation does not mean that it precludes the use of regular mathematics. Now, y2 star, I'm going to take another combination of these. I can't do the same thing, but if I play this little trick and I take 1 over 2i times y1 minus 1 over 2i times y2. Now, 1 over 2i is a constant. It's perfectly fine to use that. Let me go ahead and actually plug these in. So if I take 1 over 2i times this, I get 1 over 2i times e to the at cosine bt plus 1 over 2i e to the at sine bt. Now I'm going to take minus 1 over 2i times this, so I'll have minus 1 over 2i e to the at cosine bt. So that's just negative 1 over 2i, that term. Now minus negative 1 over 2i times this term, which will give me plus 1 over 2i, because now I'm scaling a negative by a negative 1 over 2i. Let's give me plus 1 over 2i I forgot my I here. I e to the at, I e to the at sine bt. And now when I add these, we notice that these two cancel, And what happens with these last two terms is here the I and the I cancel, and the I and the I cancel, and I have 1/2 of this plus another half of that just gives me e to the AT sine bt. And this is what we're calling y2 star. Now, again, we can keep using this linearity principle, and we can say, well, we formed two new solutions that just don't have any imaginary numbers in them. So my general solution, let that be some constant times y1 star plus some constant times y2 star, and that comes out to k1 e to the AT, cosine bt, plus k2 e to the AT sine of bt. And we just have them mixed up with the k1s and k2s, but you notice this is exactly the same solution that we claimed was the solution to a system with complex numbers. So this is why I waited till the end. It gets a little tedious with some of the algebra, but it's a really beautiful process, and it takes advantage of theorems. This is kind of what we do in mathematics. We try to utilize old things to help us devise and solve new problems.